Hello students, I Shakti Kumar, lecturer chemistry, Government SRML Model Higher Secondary School Jammu. Today going to start a new topic, that is shapes of orbitals from 11th class chemistry, unit 2nd, that is structure of atom. Let's start the topic. Atomic orbitals. What are atomic orbitals? You see, these are the shapes of different orbitals, s orbitals and p orbitals. There are also d and f type of orbitals. So the shapes of first 5 atomic orbitals are like 1s, 2s, 2px, 2py and 2pz. The probability of finding an electron in a specific region around the nucleus of an atom is determined by these orbitals. 4 different types of atomic orbitals are present. These are s, p, d and f orbitals. The value of quantum numbers is different for each atomic orbital. Now, s orbitals. This is the shape of s orbital. S orbital is non-directional and spherical orbital. The s orbitals are non-directional in nature and therefore have spherical shape. Now, p orbitals. The p orbitals have dumbbell shape. These are of 3 types: px, py and pz, and directed towards x, y and z coordinates. Here value of L is equal to 1, m equal to -1, 0 and +1. P orbitals are dumbbell shape. So let's first draw the px orbital. It is dumbbell shape, so its shape is like this towards x-axis. This is on x-axis, and second is py, which is on y-axis like this, and the third one is on z-axis like this. These 3 orbitals are directed towards x, y and z coordinates. D orbitals. As we have seen, p orbitals, which are having dumbbell shape like this. Now the d orbitals have double dumbbell shape, and d orbitals have 4 lobes, as p orbitals have 2 lobes. Now d orbitals have 4 lobes like this, and if the value of L equal to 2, then M equals to -2, -1, 0, +1 and +2. That is, d orbitals have 5 different orientations, and there are 5 d orbitals with different orientations like -1, -2, 0, +1 and +2. So these are the shapes of d orbitals, and dxz, dyz, dxy, dx square minus y square and dz square are the 5 different d orbitals. And the d orbitals, as I have told you, dumbbell shaped and have 4 lobes. If L equal to 2, the different 5 orientations are -2, -1, 0, +1, +2, and they have 5 different orientations. The 5d orbitals are dxz, dyz, dxy, dx square, y square, dx square minus y square, and finally dz square. These are the 5 different orientations, and these orbitals have 2 angular nodes where the probability of finding electrons is 0. Now let's draw the shapes of d orbitals. Let's first draw the shape of dxy orbital. In this orbital, one lobe is directed towards x and y, that is between x, y. Here, between first lobe is between xy, and the second lobe intersects the first lobe. So first lobe is between xy, this is the first lobe, and the second lobe intersects it. Now the second shape is dyz. Here the first lobe is between y and z. This is the place, y and z. The first lobe is between y and z, and the second lobe intersects the first lobe, as I have told in the first structure. So the third one is dxz, and here the first lobe is between x and z. X, this is the x, this is the z. So first lobe is between x and z. X and z. And the second lobe lies on y-axis. So the next is dx square minus y square. Here the first lobe lies on x-axis and the other lobe lies on y-axis. The first lobe lies on x-axis, this is x-axis, and the second lobe lies on y-axis. So this is the structure for dx square minus y square. Now the fifth structure is dz square. In this structure, both lobes are on z-axis. The lobe on z-axis is, the first lobe on z-axis is like this, and the other lobe is condensed. Other lobe is condensed like this, but only on z-axis, and it has a special name, donut shape or Sudar shape. So these are the 5 shapes of d orbitals. Now f orbitals. The f orbitals have double dumbbell shapes. These are of 7 types. Here you can see in this figure, what we will not discuss because it's not in our syllabus. Now, the energy of various orbitals depends on principal quantum number n and azimuthal quantum number L, and more the value of n, higher will be the energy and vice versa. In case orbitals have same value of n, when the value of n is same, that having higher n plus 1 will have higher energy. Those having higher n plus L value will have higher energy, and having lower n plus value having lower value. The increasing order of energy of various orbitals is S, P, D and F. So now, nodal surfaces or nodes. The nodal surface is a region of space in which probability of finding an electron is 0, and nodal sphere are found between 2s, 3s, 3p, 4p, 4d, 5d orbitals. These are also known as radial nodes. This is the region where the probability of finding the electron is 0, and this is called node. This is 2s orbital, and these are angular nodes. These are found in p orbitals where the probability of finding the electrons is 0, like this. On this plane, on this angular plane, the probability of finding electron is 0 in p orbital. And nodal surface is a hollow sphere region in which electrons cannot be, and this is the sphere. That the first shape which I have shown you, that was an 2D shape, but this is 3D shape, and it is basically a sphere, and the nodal surface is a hollow spherical region in which electrons cannot be present. So nodal spheres are found within 2s, 3s, 3p, 4p, 4d and 5d orbitals, and these are also known as radial nodes. Nodal planes. A nodal plane is called an angular node, which is either a plane where electrons cannot be present, and nodal planes are found within p, d, f orbitals. This is an angular node which I have shown you, and here you can see 2px, 2py and 2pz orbitals, and this is px orbital which I have shown you earlier, and this is a plane which separates these two lobes, and where the probability of electron is 0. And likely here in py, this region with white frame, where the probability of electrons is 0, and here in z orbital also you can see a frame where the probability of finding the electrons is 0. So these are the nodal planes. Now this is a 3pz orbital where we can see angular nodes and also a spherical node. Both type of nodes are present in 3pz orbital. So now degenerate orbitals. What are degenerate orbitals? The orbitals having same energy are called degenerate orbitals, and shape of p and d orbitals are given. Here we can see in 2p x, 2p y and 2pz. These are degenerate orbitals. Here 3p x, 3p y and 3p z. These are degenerate orbitals. And here in 3D you can see the degenerate orbitals. So orbitals having same energy are called degenerate orbitals. These can be of shape of p or shape of d orbitals. Now let's take the next topic, that is rules for filling electrons in orbitals and electronic configuration. Now, what is electronic configuration? It is the arrangement of electrons in the orbitals in order of increasing energies. So let's see how electrons are filled in different orbitals and what are the rules to follow before filling the electrons in orbitals. So let's discuss the rules in detail. First, Pauli's exclusion principle. It says two electrons in an atom can't have same set of 4 quantum numbers, or only 2 electrons may exist in same orbitals and these electrons must have opposite spins. Pauli's exclusion principle says that an orbital can accommodate at the maximum 2 electrons, and that too with opposite spins, and no electron has all the 4 quantum numbers same. If 3 quantum numbers are same, like n, l, m, these are same, then spin quantum number should be different. For example, say 2s square. Here n is equal to 2, l is equal to 0 and m equal to 0. But spin equal to positive and spin 2 equal to negative. So no 4 quantum numbers are same. First 3 are same, but the fourth one is different, and this satisfies Pauli's exclusion principle. Here the order is like this. This is correct. In this orbital, 2 opposite spins are taken. One is clockwise, other is anti-clockwise. But in this orbital, both the spins are clockwise, so this one is wrong. Here we can see hydrogen. Hydrogen has 1 electron, so it is filled here. And when we talk about the helium, helium has 2 electrons and one is in clockwise direction and other one is in anti-clockwise direction. So now Aufbau's principle. According to this principle, electrons are filled in orbitals in order of their increasing energies, and it means that electrons enter higher energy orbitals. So order in which orbitals are filled is like this. First we write 1s, then 2s, then 2p, then 3s, then 3p, 4s, and thereafter 3d, 4p, 5s, and then 4d, 5p, 6s, and then 4f, 5d, 6p, 7s, and thereafter 5f, 6d, 7p and 8s. This is the order which we have to follow. So the order is 1s, 2s, 1s, 2s, then 2p, then 3s, then 3p, this is 3p, 4s, after 4s there is 3d, 4p, then 5s, then 4d, 5p, 6s, and then 4f, 5d, 6p, 7s, and then 5f, 6d, 7p and 8s, like this. This is the order in which the electrons are filled in orbitals. So Aufbau's principle. So the order in which electrons are filled is like this. And here is also a rule which is followed, that is known as Bohr-Bury rules. This rule says that orbitals are filled having lower values of n plus l. Those orbitals are filled first which are having n plus l values. The value of n plus l is low and that orbital is filled first. But if similar n plus n value orbitals are present, then the orbital filled first is having lower n value. Those having, if n plus l orbitals having equal values, then the orbital having lower n value is filled first. For example, 4s, here we take 4s. 4 plus s0 equal to 4. And if we take 3d, here 3 plus d we take 2, it is 5. So 4s is filled first and 3d is filled after 4s. So if we take say 5s and 4d, 5s and 4d, which one will be filled first? 5 plus 0, 5, 4 plus 2, 6. Obviously 5s will be filled first. So the order in which orbitals are filled is this order we have to follow. Now Hund's rule of maximum multiplicity. In Hund's rule, the pairing of electron in the degenerate orbitals. What are degenerate orbitals? Orbitals belonging to same subshell. That is, the subshell can be S, P or D or F, but it should be the same. Does not take place until each orbital belonging to that subshell has got one electron. So it says that pairing is done only after each orbital belonging to the subshell has got one electron. And it is singly occupied. So here if we see example A, here we can say 1s is completely filled, 2s is completely filled. What 2p? 2p is singly filled, but here we see the opposite spin. First they should be filled with same spin, so this is wrong. If we take the case of B, here this is completely filled, this is completely filled, but in case of 2p we have to fill all the orbitals singly first and only then we can pair it. So it is also wrong. Here in this case this is filled, this is completely filled, but these singly filled orbitals having opposite spin, so it is wrong. Here this is right, this is completely filled. What, these two are doubly filled, but having the same spins, so it is wrong. Here this is the case where we see all the things are right. 1s is completely filled, 2s is completely filled, and 2p, which is first singly filled and then filled doubly by opposite spin, and so E is the right answer. So pairing of electron in the degenerate orbitals does not take place until each orbital belonging to that subshell has got one electron and it is singly occupied. So this rule we have to follow. Electronic configuration of an atoms. So what is electronic configuration? As I have told earlier, that it refers to the arrangement of electrons in different orbitals of an atom. Here we see hydrogen, atomic number 1, and electronic configuration 1s1, helium 2 and 1s2. So helium, after helium there is lithium, atomic number 3, and configuration is 1s2 and 2s1, or we can write it like helium 2s1. Then comes beryllium 4, and electronic configuration is 1s2 2s2, or helium 2s2. Here we can see the configurations of beryllium, and then boron, then carbon 6 1s2 2s2 2p6, nitrogen 7 1s2 2s2 2p3, or we can write like helium and 2p3, and then fluorine 1s2 2s2 2p5. Here is neon is 1s2 2s2 2p6, and after neon there is sodium. We can write the electron configuration of sodium like this, neon and 3s1. This is the configuration of neon. And after that magnesium 12 1s2 2s2 2p6 and 3s2. We can write it like this, in short 3s2. And then comes the argon 18 1s2 2s2 2p6 3s2 and 3p6. This is the way we write the electronic configuration